Hello there. In this video, we'll be going over exponential and logarithmic equations. So our first example is solving exponential equations. We have 5 raised to 2x minus 3 equals to 8 raised to 3x plus 1. So the first thing you always do is see if we can change both of our bases to be the same, which in this case we can, because on the left-hand side our base is 5 and the right-hand side the base is 8. There's nothing that we can change so that we get the same base on both sides. So what we can do is we can actually use the power property to bring these powers down. So what we do is we can apply a log to both sides. Now it doesn't really matter what type of log we apply. Let's say we apply natural logs, just as a standard. So let's rewrite this equation. And then we apply an ln on the left and an ln on the right. So we apply natural log, we apply the power property. These powers here come down. So we would have 2x minus 3 times ln of 5 equals to 3x plus 1 times ln of 8. So then from there what we can do is we can distribute the natural logs into the 2x minus 3 on the left and ln natural log of 8 into the 3x plus 1. So we'd have 2x ln of 5 minus 3 ln of 5 equals to 3x ln of 8 plus 1 times ln of 8. We just write as ln of 8. So we're trying to solve for x. So let's say we move anything with x over to the left side, and anything that doesn't have an x, we move it to the right side. So let's take our 3x ln of 8 and move it to the left side. So obviously we can't subtract them, so we can write this as just 2x ln of 5 minus 3x ln of 8 minus 3 ln of 5 equals to ln of 8. Now the 3 ln of 5 is a constant, so we can move that over to the right side by adding it over. So it gives us 2x ln of 5 minus 3x ln of 8 equals to, let's write this as 3 ln of 5 plus ln of 8. Now, on the left-hand side, we notice that we have both terms have an x in common. So we can factor an x out, which gives us 2 ln 5 minus 3 ln 8. And that's equal to still 3 ln of 5 plus ln of 8. Now let's go over here. So then to get x by itself, we divide both sides by the parentheses. So x equals to 3 ln of 5 plus ln of 8 divided by 2 ln of 5 minus 3 ln of 8. So that would be our solution, our exact solution. So another equation, we have e to the 3x minus 7 times e to the negative 2x equals to 4e. So first thing we do is on the left side is we need to consolidate our e's into just one single e. So we can actually use the rules for exponents. When we have e to 3x minus 7 times e to the negative 2x, we can write this as e to just 3x minus 7 plus negative 2x, so just minus 2x. Because rules for exponents, when you have same base, x to the m times x to the n, that just becomes x to the m plus n. We add the powers together. So now that we have that, we see that we can combine that. 3x minus 2x is just going to be x minus 7. And then we have 4e. So now both sides of our equation have some sort of exponential where it has a base, in this case, a base of e. So we can actually apply the inverse property to this because, remember, there is a log that's associated with e, Euler's number, and that would be natural log. So when we say ln of x, that is like saying log base e of x. So the base of that log would be e. So we apply the inverse property, so we apply an ln on both sides. So we apply an ln to the left and ln to the right. So on the left-hand side, what's going to happen is that the base of the ln and the e will cancel each other out. You're left with just the power x minus 7. Now for this right-hand side, we have to be careful because we have ln of 4e. So what we have to do is we actually have to apply the product property and split this into ln of 4 plus ln of e. Then we can say that ln of e, apply the inverse property, that's just going to give us 1. So ln of 4 plus 1 is x minus 7. And then our last step to get x by itself is add 7 to the right-hand side. So we get just ln of 4 plus 8. And that will be our exact solution. So next example, we have 5 to 2x plus 3 times 5 to the x equals to 28. So when you first look at this, we see some strange things going on because we have two exponential terms, the 5 to 2x and 5 to the x, but there's no way we can separate them in a way where we get one on the other side and one on the other because of the 28. But what we can do is think about rules for exponents, because 5 to the 2x can actually be rewritten by using the power rule of exponents as 5 to the x raised to the second power, because when you have a power raised to a power, you're actually multiplying them. So x times 2x gets us, x times 2 gets us a 2x. So that 5 to the x is important because that is what shows up right here on that second term. So what we can do is we can let some term, let's call it u, be 5 to the x, because from there we can say u squared will be 5 to the x raised to the second power, which we all know is going to be 5 to the 2x. So now when we substitute u into our equation, we're going to have u squared plus 3u equals to 28. This should be familiar because this is a quadratic equation, which we know how to solve. So we have to solve this, we have to move everything over to the left side, subtract 28 over. Minus 28 equals 0, and we can factor this. So think of two numbers that multiply to get you negative 28, but add to get you a positive 3. That would be a positive 7 and a negative 4. So u plus 7, u minus 4. Now that we factored, we set both factors separately equal to 0 and solve for u. So then that's going to give us u equals to negative 7 and u equals to 4. But we're not solving for u. We are solving for x. What we do is go back to what we set u as initially, which is 5 to the x, and we substitute it back in. So we say 5 to the x equals to negative 7, and 5 to the x equals to 4. Now our x is in the powers, so to bring them down, we apply a log to both sides. Let's say we apply ln on both sides of both equations. So to give us x ln of 5 equals to ln of negative 7. And do it on other equations as well. We have x ln of 5 equals ln of 4. However, on the first equation on the left here, we can't take an ln of negative 7. You can't take a natural log of a negative number. So we actually don't include that equation at all. We just focus on the right equation here. So x ln of 5 equals ln 4. To get x by itself, we divide both sides by ln of 5. So x equals to ln of 4 divided by ln of 5. and that would be our only solution. Now we're moving on to solving logarithmic equations. So we have log base 3 of x plus 5 times x minus 3 equals to 2. So first we need to see that the base of our log here is 3. So we can get rid of our log by raising it to whatever the base is. So we apply the inverse property and we raise the left side as 3 raised to the log base 3 of x plus 5 times x minus 3 equals to 3 to the second power, because we apply it to both sides. So on the left here, the base of our log and the base 3 of our exponential will cancel each other out, and we're left with just x plus 5 times x minus 3, and we know that on the right hand side 3 squared is just going to be 9. So now we have a quadratic, so we need to expand the left side by foiling. And if we FOIL, we get x squared minus 3x plus 5x minus 15 equals to 9. Combine like terms, x squared plus 2x minus 15 equals 9. And now we need to move the 9 over to the left-hand side. So that will give us x squared plus 2x. Negative 15 minus 9 gives us negative 24 equals 0. Now we can factor. Think of two numbers that multiply to get you negative 24, but add to get you positive 2. And that would be positive 6 and negative 4. And then we can now set both terms equal to 0 to solve for x. Let's do it up here. So x plus 6 equals 0, and x minus 4 equals 0, which gives us negative 6 and positive 4. But we always want to double check if our answers, our solutions, will work in the log. So if we plug negative 6 into x in our original equation here, so let's check by plugging x equals to negative 6, log base 3 of, so negative 6 plus 5 gives us negative 1, and then negative 6 minus 3 gives us a negative 9. And we're checking, is that equal to 2? So negative 1 times negative 9 is a positive 9. Log base 3 of 9, which is like saying log base 3 of 3 squared. And that would be 2, because the log base 3 and the 3 here will cancel. We're left with just the power, which is 2. That's good. Now let's check x equals to 4. X equals 4 should be okay as well, because we have log base 3 of 4 plus 5 is 9, and 4 minus 3 is 1, which gets you 9 again, which again gets us log base 3 of 3 squared, which is 2. So it means both solutions here will work for the equation. Now let's look at an equation where it involves natural logs. So we have natural log of 7 minus x plus natural log of 1 minus x equals to natural log of 25 minus x. So first thing we need to do is we need to consolidate our left-hand side to turn it into one singular log, because to solve log equations, ideally, is we want just a single log on both sides. So because we have a plus sign between ln of 7 minus x and ln of 1 minus x, we can associate that with the product property of logs. So we write this as ln of 7 minus x times 1 minus x. That's equal to ln of 25 minus x. Alright, so now both sides are natural logs, which is a log with a base of e, so we apply the inverse property to both sides by doing the base of the log, e, and what's going to happen is this will simplify to 7 minus x times 1 minus x equals to 25 minus x. Now we can expand the left-hand side by foiling. We get 7 minus 7x minus x plus x squared equals 25 minus x. Let's combine like terms, but let's write the left-hand side in descending order. So x squared, negative 7x minus x is negative 8x, plus 7 equals 25 minus x. And then we want to move everything over to the left-hand side, so we can add x both sides, and also subtract 25 both sides. So in doing so, we're going to get x squared, negative 8x plus x is negative 7x, and then 7 minus 25 is negative 18. And that's equal to 0. And then we can factor, take two numbers, multiply to get you negative 18, but add to get you negative 7. That would be x minus 9 and x plus 2 equals 0. So now we set both factors equal to 0 separately and solve for x. So we add 9, we get 9, and subtract 2, we get negative 2. However, if we look at x equals 9 here, if we check this by plugging it into our equation, we kind of encounter some problems. Because if we plug 9 into the x's on the left-hand side, we'll get ln of 7 minus 9 is negative 2, plus ln of 1 minus 9 is negative 8. And that causes problems because we can't take logs of negative numbers. So that means that x equals 9 would not be a solution. You can't do that. So the only solution would have to be x equals negative 2. And we can see that that's okay, because if we plug negative 2 into x on all of our logs here, we'll have a positive number, which is fine. So the only solution to this equation is x equals to negative 2. Another one we have log of x squared minus 100 minus log of x plus 10 equals to 1. So this time, even though there's only logs on the left-hand side, we don't want to move that negative log x plus 10 over to the right side because we have that constant 1 on the right-hand side. But what we can do is apply our log properties. So between the two logs, we have a minus sign, so we can associate that with the quotient property. So we can write this as one singular log of the first term, so x squared minus 100, divided by the second term, x plus 10, equals to 1. So, a couple things we can do. First things first is, let's say we try to get rid of our log. So we can get rid of it by applying the inverse property. So what is the base of log? When you see just log of x, we assume that the base is 10. So the base is 10. We would apply the inverse property on both sides by applying a 10 to the left and to the right. So what's going to happen on the left is it will simplify to just x squared minus 100 over x plus 10. And the right hand side is just going to be 10 to the 1, which is 10. Okay, so now we want to solve for x. First thing we do is we want to get rid of our denominator. So we multiply both sides by x plus 10. So left hand side, x plus 10 on top, x plus 10 on bottom will cancel. We'll have just x squared minus 100 equals to 10x plus 100. Because we distribute the 10. Now we can move everything over to the left hand side. So that will give us x squared minus 10x, and then negative 100 minus 100 is a negative 200 equal to 0. So we can factor, find two numbers that multiply to get you negative 200, but add to get you negative 10. So that would have to be a negative 20 and a positive 10. So then we set both factors equal to 0. X minus 20 equals 0. X plus 10 equals 0. Now we solve for x. We get 20. X equals 20. And x equals negative 10. Will that work though? Because if we were to plug negative 10 into x here, that gives us a problem because we're going to get, let's check, plugging x equals 10. On the left hand side, when we do x squared, negative 10 squared, that's 100 minus 100 is log of 0. Same thing here, minus another log of 0. Log of 0 is actually undefined, so that means that we cannot do that. So we cannot consider negative 20, or negative 10, I'm sorry, as our solution. So let's check for x equals 20 to be sure. We plug 20 in, so 20 squared is 400, so we have log 400 minus 100 is 300, minus log of x plus 10, so 20 plus 10, which is 30. So log of 300 minus log of 30, that's like saying, applying a quotient property, log of 300 divided by 30, which is 10, log of 10, but our base is 10, so log base 10 of 10 is actually going to be 1 because of the inverse property. So that should be okay. So the only solution that we have, let's box it in red here, would just be x equals to 20. So for logs, we always want to double check our answer and make sure that our solutions that we got make sense in the original equation. So now let's look at some applications of logarithmic and exponential equations. One of the more common exponential equations that we can apply it to is what's called exponential decay. So we look at an example here. If an Inca mummy has 1/3 of the amount of carbon-14 of a human being, how old is the mummy? Now we're given that the amount of radiocarbon present after t years is given by the equation y equals to y naught e to the negative 0.0001216 t, where y naught is the amount of carbon-14 present in living plants and animals. And we want to round our answer to the nearest whole year. So the key thing we want to look at here is that the Inca mummy has 1/3 of the amount of carbon-14 of a human being. So we can say that human being is a living plant or animal. So we say in this case that y naught or y0 could be our human. So our mummy has 1/3 amount of carbon-14. So what we can say is that because our equation here, y equals, that y represents the mummy, we can say that in this particular case, that y would actually be 1/3 of y naught, because it's 1/3 the amount of carbon of the human being. So taking this information, we can now replace y equals 1/3 y naught into our equation on the left-hand side. So substituting y as 1/3 y naught, we get 1/3 y naught equals to y naught e to the negative 0.001216 t. There's 0 here. So now we want to solve for t. The first thing you do is we can actually divide both sides by y naught. And in doing so, it cancels the y naught altogether. So we're left with just 1/3 equals to, erase this, 1/3 equals to e to the negative 0.0001216 t. So now we're trying to solve for t, our time, in years, but our variable t is actually in the exponential. So now we apply the inverse property again. So our base here is e, so we apply a natural log on both sides. So in doing so, we write it as ln of 1/3 equals to ln e to the negative 0.001216 t. So in doing so, if we were to take ln of 1/3 using a calculator, we get approximately negative 1.09861. And on the right-hand side, the ln and e, because they're inverse of each other, they go away, and we're left with just negative 0.0001216 t. And then to get t by itself, our time, we would divide both sides by that negative 0.001216. So if we're using a calculator, we divide it, we get approximately, our t would be approximately 9,034.64 years. And because we want to round to the nearest whole number, this would be approximately 9,035 years. And that will be our solution. So another common application of logarithmic and exponential equations is looking at the concentration of certain solutions. So this is often used in classes like chemistry. So we have an example here. The pH of a solution is defined as pH equals to negative log of H3O plus. So using this definition, let's determine the following. Part A says the pH of a solution with H3O plus equals to 2 times 10 to the negative 4. We want to round to nearest tenth. So what we can do is, so part A, we're given that our H3O plus is 2 times 10 to the negative 4. So our pH equation, as before, was pH was negative log of H3O plus. So all we're doing is we're replacing H3O plus with 2 times 10 to the negative 4. So we can say this is negative log of 2 times 10 to the negative 4. So all we're doing is we're just plugging this into the calculator. So we're doing negative log of 2 times 10 to the negative 4. And that gives us approximately the pH concentration, which is be 3.698. So we can say just 3.7. So that would be part A. Now part B says, what if our concentration, our pH, was 6.5? So then we would use the same equation, but replace pH with 6.5. So it would be 6.5 equals to negative log of H3O plus. And we're trying to find what the concentration of H3O plus is. So we're solving essentially for H3O plus. So first thing we do is let's move that negative over to the left side. So we divide both sides by negative 1. Just so we can just get just log on the left hand side. Or on the right hand side, I'm sorry. So it'd be negative 6.5 equals to log of H3O plus. So now, to get log the H3O plus by itself, we need to get rid of our log. So we have to identify what is the base of our log here. So as stated before, if we don't see the base of the log, we know it's going to be a base 10. So what then you do is you apply the inverse property of logs in order to get rid of our log. So we would raise this to a power of 10. So we can write this as 10 to the power of negative 6.5 equals to 10 raised to the power of log of H3O plus. So then what's going to happen on the right hand side is the base 10 and the log base 10 is going to cancel. And we're left with just H3O plus the concentration on the right hand side. And then we can calculate 10 raised to the negative 6.5. 6.5, and that gives us, so let's write this in scientific notation. This would actually be 3.16 times 10 to the negative 7. Essentially a very, very small number. And that will be our solution. So let's look at another example. During an epidemic, the number of people who have never had the disease and who are not immune decreases according to the function here. F of x equals to 15,000 e to the negative 0.05 t, where t is the time in days. How long will it take for the initial number of people not immune to decrease to half its amount. So the key thing we look at this here is this last part where it says it's half of its amount. What does that mean? So half its amount is half of what initially was, number of people who never had the disease. The initial, in this case, initial amount would be that 15,000 people. So half of that would have to be taking the 15,000 and dividing it by 2. So it gives us 7,500. That's what's called, oftentimes you would see exponential decay problems have given its half-life. So this is the half-life of it. So now what we do is we replace, we can call this our f of x, or we can call it our y, and we would have 7,500, plugging that to the left side, equals to 15,000 e to the negative 0.05 t. So now we're trying to solve for t, our time in days. We do the exact same thing as we did before. We get our e by itself, so we divide both sides by 15,000. So we know 7,500 divided by 15,000 is just going to be 1/2, equals to e to the negative 0.05 t. And then we apply ln on both sides to get rid of our exponential on the right. So we do ln of 1/2 equals to ln of e to the negative 0.05 t. So using our calculator, we take ln of 1 divided by 2. 1/2 is negative 0.6931, let's say approximately. 1. And on the right hand side, again, ln and e are inverses, so they go away and we're left with just negative 0.05 t. Then the last process is divide both sides by negative 0.05. And that gives us approximately 13.86 days. So it tells us that we would get t equals to 13.86 days, or if we were to round up to a whole number, it would be approximately 14 days for the initial number of people to not immune to decrease to half its original amount. So that would take 14 days for that to happen. And that would be our solution. So another typical example of using exponential equations would be oftentimes finance questions. So something like when trying to find the future value of something, you were trying to compound it periodically. So the future value formula when you're trying to compound something periodically is of the formula a equals to p times 1 plus r over n raised to the nt, where a is considered our future value, p is our principal, which oftentimes means that how much you're putting in initially, r is our interest rate, and then n is our compound period. And finally, t would just be our time, and that's always going to be in years. So we look at this question here. If $6,000 is invested in an account at 6% annual interest, compounded monthly, how many years will it take for the money invested to grow to $14,000? So we're trying to grow the money. We're putting in initially $6,000. So right away we can say that our principal is 6,000, and we want it to grow to 14,000. That means in the future, the value will be 14,000. So we can call that our A. Now, we know that the annual interest rate is 6%. So we say that's our R, but always remember writing interest rate should always be in decimal. So 6% as a decimal is 0.06. And then it's compounded monthly. So monthly would be our compound period, And monthly means it's because there's 12 years in a month. So we say our N here would be 12. And we're looking for how many years it will take for it to grow. So we're looking for T. So let's take everything we have and plug it into our future value formula. So we would have 14,000, which is our A, equals to P, 6,000, times 1 plus R, so 0.06, divided by 12, our compound period, raised to the N times T, so it'd just be 12T. So let's try to solve, we're trying to solve for T. So first things first is let's get rid of that 6,000 in front of our parentheses. So let's divide both sides by 6,000. So we can use our calculator here. So 14,000 divided by 6,000 gives us 2.333 repeating. So 2.333, let's get a couple threes here. Repeating equals to, now let's write, we can actually go ahead and simplify this inside here. So if we do 0.06 divided by 12, and we add 1 to that, gives us 1.005, and that's raised to the 12t power. So now, to solve for t, our t isn't actually in the exponent. So we need to bring it down somehow. So now we can bring it down by using logs. Any type of log would be good. So let's say we just use natural log, as we did before. So let's apply a natural log on both sides. So apply a natural log on our left side, natural log of 2.33 equals 2, and natural log of the 1.005 to the 12t. So what's going to happen on the right here? So the right, it's not going to, there's no inverse, so nothing's going to cancel out as before. However, we can apply the power property to this and take this power, the 12t, and just bring it down to the front of ln. So we can say this becomes 12t ln of 1.005, and the left side's still ln of 2.333 repeating. So we're trying to solve for t, so we need to get that t on the right side by itself. So we can do that by dividing, get rid of the 12 and the ln of 1.005. So divide by 12, ln of 1.005 on both sides. So in doing so, let's go over here on the right. Let's say t equals 2. So now we use our calculator. We do ln of 2.333 repeating divided by 12 times ln of 1.005. So it gives about 14.156 years. So 14.16 years. So that's how long it would take for our money that we invested $6,000 in to grow to become $14,000. So it would take approximately 14 years. All right, so let's look at another finance question. You want to invest $10,000 for your kid's college fund, and you have to choose between two investment options. Option A is invest the money in a fund that pays an average annual interest rate of 8%, compounded semi-annually. And option B is invest the money in a fund that pays an average annual interest rate of 7.75%, but compounded continuously. If each investment has a term of 18 years, which one is our best option? So, first thing we can see is let's kind of write down all information we have. So part A, option A, is we're investing with so we're initially putting in $10,000. So we say that's our principal. 10,000. We have an annual interest rate of 8%, so that's our R, and 8% is 0.08. And then compound it semi-annually. Semi-annually means twice a year. So that tells us that our n is going to be 2. And again, we'll still be using the compound formula from the last question. So that would still be a equals to p times 1 plus r over n raised to the nt. But let's look at for option B. And then, yeah, our t is still going to be 18 years. So we'll say t here is 18. Now, for part B, for option B. Option B is we're investing, but then it's the annual interest rate of 7.75%. So we say still two things we have is t is 18 and p is still going to be 10,000. But then our r is now 7.75%. So that as a decimal is 0.0775. But this time it says compounded continuously. So compound continuous is actually a separate formula. That would be for future value, that would be a equals to PE to the RT. So this time we only need the principal, the rate, and the time. We don't need the period, the n, because we're just compounding it continuously. So this is the compounded periodically, and this is the compounded continuously. Okay, so now let's calculate this. So for option A, we would plug in our formula as A equals to our principal, 10,000, times 1 plus R over N. So R was 0.08 over 2. That's compounded twice a year. Raised to the NT. So it would be 2 times our 18, which is our years. So using a calculator here, let's calculate that. So we can just plug all of this into our calculator at once. So 10,000 times 1 plus 0.08 divided by 2. And we're raising that to the power of NT. So 2 times 18 is just going to be 36. So that will give us approximately 41,039. And because this is our future value, it's money, we can round to the nearest cent. So it'd be 33.33. Because it'd be 32.5, which rounds up to 33. Now let's do option B. Apply the compounded continuously. So A equals to our same principle, 10,000. We're doing E raised to R times T. So it would be our rate, which was 0.0775. And then we're doing 18 years still. So let's plug that in. 10,000. And doing E raised to the power of 0.0775 times 18. And that gets us 40,349 point round up to 75. So that would be the future value for option B. So comparing our two future values, which one would give us a better deal? It would have to be option A, because using the compounding periodically, we will get more money out of our investment in 18 years.